All right, so we're in section 1.4 now. This is the last section in chapter 1 that we need to cover. And we're talking about continuity, specifically continuity from a calculus perspective. So just to get right into it, the concept of continuous functions, or continuity as we're putting it, is one of the fundamental subjects or fundamental concepts or topics in calculus. We talk about functions having this property that we call continuity, and lots of the implications of that. So there's different ways of approaching this concept with varying degrees of formality and precision. Usually the first way we introduce continuity is by looking at graphs of functions and talking about how or what continuity looks like in a graph. So if you consider these two graphs right here, this is an example of a continuous function. And the reason why is because if I were to draw this curve using my pen, just kind of going from left to right, I can draw the entire thing without ever picking up my pen, okay? Whereas in this second picture, if I wanted to sketch this curve, I notice that it's in two separate pieces. So if I were to try to sketch it from left to right, I could get about this far, then I'm gonna have to lift up my pen and come down here to complete the rest of it. That is a good way of understanding continuity, at least from a graphical perspective. It's not a good way of understanding it in the long term, because it's not a very precise way of defining continuity. So what we're going to do instead is give a more complete definition of what continuity means. But as far as this definition goes, we can sort of think of continuity, or a function being continuous, as one for which we can sketch the graph without having to pick up our pen. Or in other words, there are no breaks or holes or vertical asymptotes or things like that that break the graph into pieces. Now, returning to this one, it's a little bit too hasty to just say this function is not continuous or doesn't have continuity, because parts of it do have continuity. So if I'm only concerned about this part of the graph, it is continuous on this interval here, from negative infinity up to 1. But I have what's called a discontinuity when x is equal to 1. And then after that, I have this other piece which by itself is continuous. But taken together, I could say that this graph has a discontinuity at x equals 1, or it's discontinuous at x equals 1. So we tend to be a little bit more specific than just that. All right. Let's talk about a little bit more complete of a definition of continuity. So a function f is called continuous at a point where x is equal to c if and only if the following three conditions are satisfied. All of these need to be satisfied simultaneously. First of all, f of c needs to be defined. So in other words, c needs to be in the domain of this function in order for it to be continuous there at all. In addition to that, the limit as x approaches that same number c of f of x has to exist. We've seen examples where limits can fail to exist for various different reasons. But for continuity to take place, the limit as x approaches c of f of x has to exist. Finally, step 3 is a way of relating steps 1 and 2, or conditions 1 and 2. It says that limit that we established exists up here as x approaches c of f of x has to be equal to f of c. So not only does f of c have to be defined and this limit have to exist, but they have to equal each other. Okay, so I'm going to show you on the next page some graphs where we don't have continuity. It's a little bit easier to understand this definition when we see one of these conditions failing. Okay, so let's come over here. Okay, this first graph is not continuous, and it may be a little bit difficult to see on the video, but right here there's a hole in the graph. You may or may not be able to see that, but there's a hole right there. So this function, when I graph it, I actually can't draw the graph without picking up my pen, because I have to pick it up to draw that hole right there. There's a space that's missing, okay? So in this case, if I look here on the x-axis, I see a number c. So this is saying that f of c is not defined. Whoops, sorry about that. Because if I try to plug c into my function, there's no point there. There's a hole. There's no point elsewhere either. So f of c does not exist in this case. This example, it's clearly not continuous. The graph is broken into two separate pieces. In this case, the function is defined at c. I have a point here, but it's the limit as x approaches c of f of x does not exist. And the reason why is because if I were to take my two one-sided limits, as I approach c from the left, this part of my function is approaching some y value way up here, while as I approach from the right, it's approaching a different y value down here. So the one-sided limits disagree with each other, which is giving me discontinuity at c, okay? So, and we know that that means that the two-sided limit does not exist. Finally, here's an example of the third condition failing, where we still get discontinuity. So in this case, f of c is defined because if you see c down here, if I plug f into it, there's a point right here. So I can see that f of c has a value given by the y-coordinate of that point. Also, the limit as x approaches c exists because where this hole is, that's right over c, if I approach from the left or as I approach from the right, in both directions we're approaching the same y value here. So that limit does exist. However, those two things are not equal to each other. F of c is equal to whatever this y value is, and the limit as x approaches c of f of x is equal to this other y value up here. They disagree, so we would say that this function is discontinuous at c. And hopefully you can see from each of these graphs, even if we didn't have this definition, why each of those graphs are not continuous at c, whether we have a hole or a jump or a hole and a point, but they don't align, okay? So that's why we need those three conditions in order for continuity to take place. Now, how do we decide or determine whether a function has continuity at a point? It depends on what information you're given about that function. But basically, here's a step-by-step process. First thing you want to do is check and see if f of c is defined. Because if it's not, right away that first condition is not met, and we can just say, nope, not continuous. But really what that's doing is that's checking to see if this number c is in the domain of a function. Remember, the domain is the set of all possible inputs, the set of all things I can plug into it. So if c is not in the domain of a function, then it can't be continuous there because it's not even defined there in the first place. Secondly, if f of c is defined, we move on to step 2. So if the next step is to check the limit as x approaches c of f of x. And we've done plenty of examples of this throughout chapter 1. So sometimes you need to compute two separate one-sided limits and see if they agree. For example, in the case of a piecewise function, we might need to do that. Or use any of the other approaches that we've talked about. If that limit does not exist for whatever reason, then we have not met that second condition for continuity, and we can say at that point, this is not continuous. Okay, and remember, it can fail to exist for different reasons, including vertical asymptotes. So we'll see examples of that. But if that limit does exist, then we move on to this third step. And in this third step, we're just using our previous two results. Is f of c defined? And if so, what is it? What happens when I plug c into my function? And is that limit defined? And if so, what is it? I compare those two things, and if they are not equal to each other, then we can say that our function is not continuous because that's the third condition. They have to be equal to each other. If they are equal to each other, then we get to say, yes, our function is continuous at x equals c. So let's take a look at an example where we have a function to work with. This is the function y equals f of x. We want to determine where it is discontinuous. So first of all, I could say it's definitely not continuous at x equals 1 because I see a hole in the graph here, okay? So I could say discontinuity at x equals 1. And we need a reason why. Because f of 1 doesn't exist. So that's one of my answers. It doesn't exist because even though there's a hole there, I'm also not seeing a point anywhere above 1. So that must mean that, you know, based on what I can see, at least in this part of the graph, that f of 1 is not even defined. Okay. Next up, I have a break in my graph right here at x equals 3. So I can say that there is a discontinuity at x equals 3. And why is that one a discontinuity? What's my justification? Well, as you can see, if we approach 3 from the left, I get one value all the way down here. If we approach 3 from the right, I get a different value way up here. So what that's saying is that my left and right-handed limits are disagreeing with each other, which means the two-sided limit does not exist. It's failing condition 2. So because the limit as x approaches 3 of f of x does not exist. I'm going to use D and E for that. Okay? What else can we say? There's also a discontinuity right here at 5, and it's apparent because there's a hole in our graph. But of those 3 conditions, which one is failing right now? Well, the limit as x approaches 5 exists this time, because as I approach from the left and as I approach from the right, in both cases, we're approaching this hole, which has just a single y value to it. So that limit does exist. F of 5 also exists because there's a point up here. So whatever the y coordinate of that point is, that's what f of 5 would be equal to. Both of those things exist, but they are not equal to each other. The limit gives me a y value down here, and f of 5 gives me a different y value way up here. So this time, I'm going to say that there is a discontinuity at x equals 5 because the limit as x approaches 5 of f of x is not equal to f of 5. So in this one example, we're seeing all 3 cases of a condition for continuity failing. And we're able to identify the discontinuities of this graph. Aside from x equals 1, 3, and 5, in all those other areas, the graph does appear to be continuous. So we found all 3 that we were meant to find. Okay? Down here, I want to look again at some of the different types of continuities. Now, I don't actually think our book uses these terms. I'm getting these terms from a different calculus book, but they're very common terms to use. So you might hear me use them here or there, but if you don't know them, if you don't remember them after this section, it's not going to hurt you for the course. So in the first and second graphs here, we have what are called removable discontinuities. And those are discontinuities where the limit as x approaches our value exists, but it's not equal to f of that value. Whether because f of that value, in this case it's 2, so I'm just going to say 2. Here, the limit as x approaches 2 exists, but f of 2 does not exist, so they can't be equal to each other. Here, the limit as x approaches 2 of f of x exists, and f of 2 exists as well, but they're not equal to each other. So when we get that third condition failing, where the limit exists, f of c exists, but they're equal to different things, that's where we get what's called a removable discontinuity. Now, the reason it's called a removable discontinuity is because you can literally remove it if you were to stick a point right there. Okay, so if you were to put a point in that hole, it will close the gap and create a continuous function. That would be removing the discontinuity by doing that. Okay, the other 2 types of discontinuities we encounter a lot, and these are not the only types. There are actually other types, they're just less common. One is an infinite discontinuity. That's where we get vertical asymptotes of some kind. So this function is, we have this vertical asymptote where as I approach from the left or as I approach from the right, my function is going to infinity. It could also go to negative infinity. It could also do different things on each side. One can go to negative infinity while the other goes to positive. But in all of those cases, we say that we have an infinite discontinuity. In this example, there actually is a point here at 0. So f of 0 is defined, but we still have a vertical asymptote at x equals 0, which is apparent from the left and right branches of this curve. So oftentimes there won't be a point here, but this is just showing that it's possible that a point can exist there. And then finally, we have these things called jump discontinuities. These are the cases where a function will have a discontinuity at a value when the left and right hand limits at that value both exist, but they go to different places. So notice here, as x approaches 0 from the left, f of x is going down to this hole right here. But if we approach 0 from the right, it's going towards the origin up here. So different values. Even though both one-sided limits exist, the two-sided limit fails to exist. That's where we get this jump discontinuity. Again, not super important that you know those terms, but it is good to be familiar with different ways in which a function can fail to be continuous. All right, so far we've looked at that definition for continuity, and we've focused primarily, when we're examining continuity on like graphs of functions. We've been resorting mostly to examining a graph, but a lot of the time you're not given a graph to work with. Instead, we may be given like an algebraic representation for a function. So the question is, how do we determine where those types of functions are continuous? And the really, really important thing that's going to help us here is this theorem that I have stated right here, theorem 1.6. This is as it appears in your book. So it says that polynomials, rational functions, power functions, exponential functions, logarithmic functions, and any combination of these are always continuous on their domain. When we say combinations of these, what we mean is when you take functions of any one of these types and you combine them by adding, subtracting, multiplying, dividing, composing as functions, raising one function to another function as an exponent, any way that you can operate on functions to combine them together, the result will also always be continuous on its domain, okay? That's a really powerful theorem because if we know what the domains of these functions are, then we automatically know what values they're continuous for, because those two sets of numbers would be the same. An important thing to pay attention to with this function, or this theorem does not say that all of these functions are continuous for every possible value of x. It specifically says on their domain. Some of these functions that fall into these different categories may have restrictions on their domains. For example, we know that the natural logarithm, y equals the natural log of x, or really any logarithm for that matter, cannot take non-positive numbers as inputs. You can't plug a -1 into a natural log function. So there's a domain restriction there, which means it's not even defined for all real numbers, so it can't be continuous for all real numbers. Here's a different example, the function y equals 1 over x minus 2. This function is continuous everywhere on its domain, which is different from saying it's continuous for every value of x, because this function is not defined when x is equal to 2. I would be dividing by 0 in that case, and in fact, the graph of this function would have a vertical asymptote there. So this is not defined at 2, and therefore it's not continuous at 2. But that's actually the only value for this function that we can't use for x. It's defined for all other values of x, and according to this theorem, that would mean that it's also continuous for all of those values of x. So determining whether a function of the type being described here in this theorem is continuous or not is a question of just finding its domain. So I want to do an example down here where we're doing exactly that, finding the domains of these different functions, because that is where they will be continuous. So we want to find where each of these 4 functions here are continuous. Now you're going to notice these functions can look really, really nasty. And the trick is to not get too caught up in how nasty they look. Typically, there's only specific parts of these functions that we're supposed to be looking at to determine continuity. So for example, this first problem right here, part A, I'm looking at a rational function. It's a polynomial over another polynomial, right? If I'm only concerned about the domain of this function, then what I'm really doing is I'm asking, what am I not allowed to plug in for x here? Well, I know for rational functions, the only real issue we run into is dividing by 0. I need to make sure that I don't plug in any values of x which would cause me to divide by 0. So what I'm going to do is try to figure out what would cause this denominator to equal 0. And it will help me to factor it. Now, x squared plus 25 is a difference of squares. It's going to factor to x minus 5 times x plus 5. If I wanted to be really, really thorough here, I would take that denominator and I would come over here and I would set it equal to 0, and then I would do a bunch of steps to show what the solutions for that are. But at this point, because this is calculus, we shouldn't have to do all of that work. I should be able to look at this and say, well, if x is equal to 5, then the denominator will be 0. I can't use that. If x is equal to negative 5, then again, I'll get a 0 here. I'm dividing by 0, can't do that. So x cannot equal either plus or minus 5, either of those. Now, it is allowed to equal anything else. Those are the only issues for this function. So I'm ready to write out what the domain of this function is, because that's also the set on which this function is continuous. But we don't write it this way. This is a good way of kind of thinking about what the set on which this function is continuous. But if you notice here, it specifically says give your answer in interval notation. So here's what interval notation looks like. Sometimes it helps to use a number line, which we're going to use a lot. Take the two numbers that we know are not in the domain of this function, negative 5 and 5. Okay, and then up above this number line, I'm going to sort of do a one-dimensional graph of all of the values that are in the domain of this function. So negative 5 is not a part of that function, but everything to the left of it is. And positive 5 is not in the domain of that function, but everything between negative 5 and positive 5 is. So that line indicates that. And also everything that's greater than 5 or to the right of 5 on this number line is also in the domain of this function. So this is a graphical representation of my domain. It's still not interval notation, but the way I get interval notation from this is that I look at the pieces that this graph is broken into. I have 1, 2, 3 pieces. Each of those is can be denoted by an interval. So the first one, negative infinity to negative 5. That's interval notation for this little branch right here. I'm using parentheses as opposed to square brackets because square brackets would indicate that the endpoints are included in that, and I don't want negative 5 included because we have a hole there. This guy right here, this little line segment between the two holes, that's the interval negative 5 to 5. So I'm going to notate it this way. That's interval notation. And then from here, from 5 to infinity, but not including 5. Sorry, my dog's making a bunch of noise. That's also included in the domain of that function. When we have multiple intervals, all of which give us values in the domain of our function, we join them together with these capital U's, which stands for union. This is the union of intervals. So this is actually the way that we want to write the domain of this function. And again, when we're looking at rational functions, the domain is the same thing as the set of values for which our function is continuous. Again, that's what that theorem up above said. So we have one answer already. Now let's look at part B. So I'm looking at part B here, and I'm seeing y equals the natural log of 15 minus 3x plus the square root of 6x minus 1. So what I'm looking at here is values of x for which this function is not defined. And this function has kind of two parts to it. There's the natural log, and then there's the square root. Both of those guys have domain restrictions. I can't plug whatever I want into a natural log, and I can't plug whatever I want into a radical function, specifically a square root function. So let's look at what things we can plug in and what things we can't. Starting with the natural log. One thing I know about natural log and any other logarithm is that I have to plug in positive numbers. So this thing inside here, the 15 minus 3x, must be greater than 0. That's a requirement if this logarithm is going to be defined. This is an inequality. I can solve that for x. So I would add the x to this side, divide both sides by 3. I can rearrange some things if I want. This is going to end up giving me x is less than 5. Okay? We'll worry about what that looks like in a moment. But let's now go over to this radical function right here. This has a domain restriction as well. This 6x minus 1, which we call the radicand, has to be non-negative because you cannot take the square root of negative numbers, not without getting into a conversation on complex numbers, which we don't deal with in this class. So that means that 6x minus 1 has to be greater than or equal to 0. And make sure you note the difference. You cannot plug 0 into a logarithm, but you can plug 0 into a square root function. That's why we have the or equal to 0 here, and we don't have it here. So this I can also solve pretty easily, and I'm not doing every individual step because you should be able to do that. We get x is greater than or equal to 1/6. Okay. Now I kind of have two different conditions on my x when I'm looking at the domain of this function, and both of them have to be simultaneously satisfied in order for my function to have continuity. So if we look at that, plot the two relevant values for x, 5 and 1/6. 1/6 would be over here. 5 is going to be like over here. All right, and now what I'm going to do is sketch on my graph both of these inequalities. So I'm saying x is less than 5, open circle to show that it's strictly less than 5. X is greater than or equal to 1/6. Because it's greater than or equal to, I use a closed dot. I don't use an open circle. Okay. If a number is going to be in the domain of this function, it has to satisfy both of these simultaneously, because that's great if I'm allowed to plug in, say, 0 into this function, right? The logarithm, because that would just give me the natural log of 15 if I plug a 0 in for x. I know that's defined, but I can't plug that 0 into this function. 6 times 0 minus 1 would be -1. That's not defined. So when we're looking at this graph here, we specifically want to look at the parts of the graph where I have points on both of these like lines that I drew. And really what that amounts to is finding the overlap between them, okay? So I can see that this segment in the middle here is the overlap between those two graphs. But in interval notation, what does that look like? Well, we're including the 1/6 because the value 1/6 is on both lines. So I use a square bracket there. And then we go all the way to 5, but we don't include that endpoint of 5 in our domain because it's not a part of this lower line, even though it's a part of the higher line. That means I would use what's called a half open interval to notate my domain here. Okay, that's what I'm going to get for that function. Okay, we'll do the other two examples in the next video because this one is getting a little bit long.